Hello, today I'm going to present our recent work on compressive estimation of near-field channels for ultramassive MIMO wideband terahertz system. This paper is accepted for presentation at ICAS 2023. This work is done by me, Simon Tarbush, a researcher from Damascus, Syria. Dr. Anum Ali is with Samsung Research America, Texas, United States of America, and Professor Tariq Al-Nafouri is with King Abdullah University of Science and Technology, Thual, Mecca Province, Saudi Arabia. The terahertz band is a promising enabler for the sixth-generation networks. Specifically, terahertz can satisfy the extreme throughput requirement of up to terabits per second due to the large bandwidths available. The terahertz channel propagation is dominated by the line-of-sight component in many scenarios, and terahertz multipass components, if exist, are typically less than 10. Therefore, the terahertz channels are extremely sparse, which encourages using compressed sensing strategies for channel estimation. Moreover, the communication distance is limited to the very high free space path loss. Thus, ultramassive MIMO arrays at both ends are necessary to get high beamforming gain and achieve longer communication distances. Consequently, the use of short wavelengths, large arrays, and limited communication distance implies that the communication is near-field, where the appropriate channel model for near-field is the spherical wave model. This is different from far-field communication, where the planar wave model is sufficient for channel modeling. The spherical wave model accurately models the curvature of the transmitted wavefronts and captures the magnitude and phase variations of the received signal across the antenna elements. A simpler alternative is a hybrid spherical planar wave model, for short HSPM. This model provides a good trade-off in modeling accuracy and complexity. In this work, we propose a dictionary reduction-based compressed sensing method to exploit the geometric structure of our problem and benefit from the spatial information extracted from the estimates of the first subarray in a channel estimation of subsequent subarrays. We employ a wideband channel and system model with subconnected array of subarrays architecture. The RF precoders and combiners are implemented using finite resolution phase shifters, respecting terahertz hardware constraints. We assume that the TX is equipped with QT subarrays, distributed over the vertical and horizontal dimensions, and every TX subarray is composed of a uniform planar array consisting of Q bar T tightly backed antenna elements. Now, to model the array of subarray channel, we use the HSPM. This model captures only the phase variation across the nearby antenna elements, but captures both the phase and magnitude variations across more separated antenna elements. Thus, HSPM is particularly suitable for hybrid beamforming array of subarray architecture, where the elements within a subarray can be considered nearby antenna elements and modeled using planar wave model, whereas elements across the subarrays can be considered more separated and modeled using the spherical wave model. With this model, the MIMO channel between Rx subarray QR and TX subarray QT at subcarrier K is given by this equation. We note that 3D distance, angle of arrival, and angle of departure vary across the subarrays. Therefore, we expect that channel between different subarrays is similar, albeit not identical. This encourages benefiting from prior estimation information. The proposed channel estimation strategy consists of two main phases. The first one is the pilot transmission using random beamformers and combiners. At the end of this stage, we get the received signal vector between the Rx subarray QR and the TX subarray QT at subcarrier K, equal to a terms related to the transmission power multiplied by the measurement matrix multiplied by the quantized dictionary matrix, equal to the Kronecker product between TX and Rx dictionaries. Each dictionary consists of beams spanning the full space. Those terms are multiplied by a sparse vector containing L-bar non-zero elements that we need to estimate, and this vector varies across the subarrays. Plus, the last term is related to noise. Now, the second phase of this proposal is to perform compressed sensing-based channel estimation for the first TX-RX subarray and enhanced channel estimation using the proposed dictionary reduction method for the remaining RX subarrays, where the search space is reduced based on the prior information. Now, let's move to explain the dictionary reduction method. For a specific TX subarray, the dictionary reduction consists of the following 4 stages. We start by solving the compressed sensing problem of 1 for the first TX-RX subarray by using, for example, SOMP or OMP algorithms with input signal Y11. Then, we construct an oversampled dictionary by a factor GOVS. After that, we return from that oversampled dictionary only GDR columns that correspond to spatial angles centered around the estimated AOD and AOA of the reference subarray. Then, for the remaining RX subarrays, we solve the compressed sensing problem, but this time using the reduced dictionary. For the remaining TX subarrays, we repeat the dictionary reduction estimation method. We simulate a line-of-sight terahertz channel. The simulation parameters are listed in this table. We compare the performance of 2 traditional compressed sensing algorithms, OMP and SOMP, with and without the proposed DR. In the first figure, we plot the normalized mean square error versus the signal-to-noise ratio. From this figure, we note that the proposed DR has up to 2 dB improvement over conventional method in high SNR. In the second figure, we plot the effective achievable rate versus the number of TX measurements. Both OMP and SOMP with DR achieve higher effective achievable rate than both conventional methods. As a conclusion of this work, we proposed a compressive channel estimation strategy for Massive-MIMO terahertz system with the array-of-subarray architecture. Using an HSPM, the proposed strategy outperforms both OMP and SOMP and achieves a low NMSE and effective achievable rate close to the perfect channel case. The references used in this presentation are listed here. Thank you for listening to my presentation. Please feel free to reach out for any further questions.